Come with me. Let's journey into the heart of the atom, a realm of incredible energy and complexity. A universe in miniature, where the fundamental forces of nature are locked in an eternal dance, constantly interacting and shaping the very fabric of reality. For most of history, this realm was invisible, a hidden world beyond our direct perception. Its secrets remained hidden, veiled by the intricate and often counterintuitive laws of physics. But in a flash of insight and ingenuity, we learned to peer inside, breaking through the barriers of the unknown. And we discovered that the atom held a power to rival the stars themselves, a source of immense energy waiting to be unleashed. This profound revelation forced humanity to confront a monumental choice. Could we harness this atomic energy for creation, for the betterment of humankind? Or would we succumb to the temptation of destruction, unleashing its devastating potential upon the world? We unlocked a fundamental secret of matter and energy, a key to understanding the universe itself. This secret was elegantly captured in Einstein's famous equation, E equals mc squared. Mass is energy, a concept that revolutionized our understanding of the cosmos, and by carefully manipulating the atom, we could release a fraction of that immense energy, tapping into a power source unlike any other, enough to power entire cities, illuminating the darkness with the promise of progress, or tragically enough to utterly destroy them, leaving behind only devastation and despair. The atom's power is the very same force that fuels our sun, the engine of our solar system. It's constantly converting matter into pure energy, radiating light and warmth across the vast expanse of space every second. By learning the atom's deepest secrets, we essentially captured a piece of a star, bringing its power down to Earth. A star contained within a jar, a testament to human curiosity and scientific achievement. But holding a star is inherently dangerous. Its immense power demands respect and caution. Its fire can warm and sustain, providing energy for countless applications, or it can consume everything in its path, leaving behind only ashes and devastation. This inherent duality defines the nuclear age, a constant tension between potential and peril. It stands as a testament to our boundless ingenuity, our ability to unravel the mysteries of the universe. But it also serves as a stark warning of our capacity for destruction, a reminder of the awesome responsibility that comes with such power. How did we achieve this? How did humanity unlock the secrets of the atom? The story involves brilliant minds pushing the boundaries of knowledge, global conflict that spurred unprecedented scientific advancement, and a fundamental understanding of how atoms can be manipulated, either to split apart or to fuse together. To truly understand the devastating power of the bomb, we must first understand the two distinct paths that lead to the release of atomic energy, each with its own unique characteristics. One path involves splitting something heavy, like a uranium atom, into smaller components. The other path involves fusing something light, like hydrogen atoms, together to form a heavier element. Both of these processes, fission and fusion, lead to the release of explosive power, a force that can reshape the world. But they achieve this through very different routes, each governed by its own set of physical laws and constraints. So, let's embark on a journey to explore these two fascinating paths, unraveling the mysteries of atomic energy along the way. Imagine the nucleus of a heavy atom, something incredibly dense and complex, like uranium. It's a tightly packed core, brimming with potential energy. Crowded, unstable, and constantly vibrating with internal forces, it's ready to burst at any moment. This inherent instability is key to understanding fission. This is fission, the process of splitting a heavy nucleus into smaller, more stable pieces. It's like carefully cracking a fragile vase. When a uranium nucleus splits, after being struck by a neutron, the resulting fragments, the daughter nuclei, weigh slightly less than the original uranium nucleus. That missing mass doesn't just disappear, it becomes a burst of energy, a tremendous release, as Einstein predicted with his famous equation, EMC2. This is the secret of the atomic bomb's devastating power, a force unlike anything seen before, tapping the very fabric of matter, unlocking the energy binding the nucleus together. Now let's shift gears and consider fusion, the opposite of fission. This involves forcing light atoms, like isotopes of hydrogen, to violently join together, overcoming their natural repulsion. This is the very process that powers the sun, our star, and all the stars in the universe. Hydrogen nuclei are relentlessly fusing into helium, releasing incredible amounts of energy in the process. This happens under immense heat and pressure, conditions that are hard to imagine here on Earth. A hydrogen bomb replicates this process on Earth, creating a miniature star, if only for a fleeting moment. Fusion, like fission, also results in a loss of mass during the reaction. That mass is converted into even more energy than fission, making it an incredibly potent force. That's precisely why fusion bombs, also known as thermonuclear weapons, are vastly more powerful and destructive. Fission breaks things apart, splitting heavy atoms into lighter ones. Fusion, on the other hand, builds them up, forcing light atoms to combine into heavier ones. Both processes, however different, unlock the immense energy stored within the atomic nucleus, unleashing cosmic-scale explosions demonstrating the raw power contained within the atom. These two fundamental processes, fission and fusion, are the underlying keys to both nuclear power generation and the creation of nuclear weapons. Therefore, understanding them is absolutely essential to understanding the science behind the bomb and its devastating potential. Next, let's delve deeper and see how a chain reaction, a self-sustaining cascade of nuclear events, turns atomic theory into a terrifying reality. Splitting just one atom releases a tiny amount of energy, a minuscule burst. But a bomb doesn't rely on just one atom, it requires trillions upon trillions of atoms. These atoms must be splitting all at once in a rapid, escalating process, a chain reaction. Picture a line of dominoes carefully arranged and waiting. One falls, triggering the next in a cascading sequence. In a fission bomb, this process is initiated when a stray neutron starts the process. When a neutron, a subatomic particle, hits a uranium nucleus, it splits the nucleus, releasing energy and, crucially, more neutrons. Each newly released neutron can then split more nuclei, continuing the chain, doubling and redoubling the reaction in a runaway cascade, an exponential surge. This rapidly escalating chain reaction is the engine that drives a fission explosion. But it only works if you have a sufficient amount of fissionable material, critical mass. Too little uranium and too many neutrons escape the mass without hitting other nuclei. The reaction fizzles out, unable to sustain itself. But reach critical mass, and the chain reaction becomes self-sustaining, amplifying rapidly. Therefore, bombs start with multiple subcritical pieces of uranium or plutonium, slammed together with incredible force by a conventional explosive trigger to rapidly form a single supercritical mass. At that instant, the chain reaction erupts with unimaginable speed and a devastating atomic explosion is inevitable, releasing tremendous energy. The underlying science, while complex in its details, is simple in its concept, but the consequences of its application are profoundly destructive and far-reaching. This is the fundamental principle of how a fission bomb works, by unleashing and controlling a self-sustaining chain reaction of nuclear fission. But fusion bombs take this destructive potential to an entirely different and even more terrifying level. If a fission bomb is a contained force, a hydrogen bomb is a small sun. It uses a two-stage process. A fission bomb triggers a much larger fusion reaction. This design, called the Teller-Ulam configuration, starts with a primary fission explosion. The blast releases X-rays, compressing and heating a secondary stage filled with fusion fuel, lithium deuteride. A spark plug of plutonium inside the secondary ignites, providing the heat to start fusion. The hydrogen nuclei fuse, releasing a torrent of energy, hundreds or thousands of times more powerful than the fission trigger. This is the terrifying power of the hydrogen bomb. To find the origin of these weapons, we travel back to World War II. In the late 1930s, physicists discovered nuclear fission, realizing it could create a weapon of unprecedented power. Fearing Nazi Germany would build such a bomb, scientists like Einstein and Szilard urged the US to act. The result? The Manhattan Project, a secret effort to build the atomic bomb, led by J. Robert Oppenheimer in Los Alamos. They overcame immense scientific and engineering challenges, racing to produce enough fissionable material and design reliable bomb mechanisms. On July 16, 1945, the first atomic bomb was detonated at Trinity, changing the world forever. The atomic age had begun. The atomic age brought a new fear: global nuclear war. To manage this danger, nations began negotiating treaties, starting with the Non-Proliferation Treaty, NPT, in 1970. The NPT aimed to stop the spread of nuclear weapons, promote disarmament, and allow peaceful nuclear technology. Other agreements like SALT and START limited arsenals and reduced risks. International organizations like the IAEA verify that nuclear materials aren't diverted for weapons. These safeguards aren't perfect, but they represent humanity's effort to choose cooperation over catastrophe. The challenge of nuclear weapons remains, demanding constant vigilance. The energy in a single kilogram of uranium equals 17,000 tons of TNT. Fusion bombs are even more staggering. One explosion can exceed all the explosives used in World War II. This is the power of the cosmos brought to Earth. Our understanding of this power is a triumph of human intellect, but also a cautionary tale. The same discovery that promises limitless energy also threatens our existence. The nuclear bomb is the ultimate paradox, creation and destruction in one. The knowledge can't be unlearned, but the choice to use it is always ours. We are living this story now. Our future depends on the choices we make. The lesson is clear. Vigilance, cooperation, and restraint are essential. We must ensure these weapons of cosmic fire are never used again.